All right, we're going to start talking about second-order linear constant coefficient differential equations. So the idea is we'll look at a differential equation of the form, so let's call that K, where we have constant times the function in each of its derivatives. So M, B, and K are constants. And here I'm going to treat x as a function of t. So the question is what function is going to satisfy an equation of that form? And we're going to talk a little bit about how we make those choices, but there's going to be a couple ways. And it's basically going to rest on the idea that we're going to guess a solution, and it's going to be in a general form. Then we're going to plug into the equation. And then we're going to ask, what does it imply about our function or our guess? Okay. Before we do that, I'm just going to give some motivation here. And this is a really important class of equations, and we're going to see that they're used for circuits, but also for physical systems. And the reason this comes up in physical systems is basically Newton's second law. And Newton's second law is that the rate of change of momentum, I cannot spell, momentum is proportional to the net force. So the momentum is given by the mass times the velocity, and its rate of change is the derivative of that, and the net force is just the sum of all forces acting on this. And when we say two things are proportional, that means there's some constant, or to use case, we'll call it C, where this relationship is true. And what happens is we define our units. What is a Newton? What is a meter and a second? All those units are defined to be consistent so that that constant of proportionality is 1. Okay, so how does this come up? So the example here is what we're going to call a horizontal spring mass system. And it's going to be really important for you to understand how these things are derived, and being able to derive it yourself and not just memorize these results. Because when in the homework and in quizzes and the final, you're not going to see something exactly like this. There's going to be some small change, and the question is going to be, can you recognize that change and deal with it? So the idea is this. I've got a horizontal table, and on this table I have some mass. And there's going to be some wall, and this mass is going to be attached to this structure via some spring. And this spring is going to have some constant associated with it. We're going to assume Hooke's law, which is another way of saying it's a linear spring. We'll discuss that later. And we're going to either set this mass in motion or pull it back or push it in, and then ask, what is its position? So we've got to define what that means. So for the position, we are going to first determine the origin. And we're going to call 0, x equals 0, the equilibrium point. So this is where this spring basically wants to naturally be without being deflected or compressed or pulled out. And the idea is this. So now I have this spring mass system. I have my origin. And if I pull it away or pull it out, at any given time is going to have some position. And we want to know what's going on with the position of this thing. So this position, we can also refer to it as the displacement. And if this is the positive direction, if I push the spring mass system in and it's to the left, that's going to be negative displacement. If it's to the right, we're going to call that positive displacement. So the very first thing we're going to do is a free body diagram. So we've got our mass, and in terms of the forces acting on it, we're going to have the force of gravity pulling down. We're going to have some normal force, the table pushing up on the mass. And we're going to have some force due to the spring. I'm going to figure that out. And we're going to have force of friction. And in this case, we're going to look at a very specific kind of force of friction. We're not to the place yet where we can deal with the friction due to the table. We're going to get there. But before we do that, we're going to assume that we're only dealing with air friction. And so now for air friction, and this is just a modeling assumption. There's different ways to do this. We're going to assume that the force of friction due to the air is going to be proportional to the velocity. So the idea being is if you double the velocity, you're going to double the force of friction. If you reduce the velocity, you're going to reduce the force of friction. And the force of friction has to be in the opposite direction of the motion because it's going to be opposing the direction. So because it's proportional, there's going to be some constant. We'll call it B. And by convention, we're going to put a negative sign there. So that's going to assume that B is a constant and, like, be careful, greater than or equal to 0. So that means that our force of friction then is going to be a horizontal force. Okay? And we're going to assume that M is a constant. Okay. So based on this, so again, we have our free body diagram. We've got the force of friction down. We've got the normal force up. Force due to friction is going to be minus BV. And then we're going to have the force due to the spring. In the vertical direction, we're going to assume that the acceleration in the y direction is 0 and the velocity in the y direction is 0. So we're going to assume it stays on the table. If that's the case, then the derivative of the mass times the velocity in the y direction is going to be equal to, so we have the normal force up minus mg. And now since the velocity is 0, we're going to have 0 equals the normal force minus mg, which says that the normal force is equal to mg. All right, we're not going to make much use of this now, but later on, if we want to talk about force of friction to the table, we're going to end up needing that. For the horizontal direction, we're going to have our momentum in the x direction. So that's mass times the velocity in the x direction. That's going to be equal to, so we're going to have, so the way I drew this, I'm going to have force due to the spring plus the force due to friction. So now the question is, what are these things? And I'm going to focus on the spring first. And we're going to use Hooke's law, which is that the force for the spring is, let me say, is proportional to the displacement. And in this case, our displacement is going to be x of t minus the equilibrium position. But we just said we define the equilibrium position to be 0. So the force due to the spring is proportional to the position. Now I've got to be careful here. If I pull, right, if this is 0 and I pull my mass out, then the force due to the spring is just going to want to pull it back in. So here we have positive displacement, and the force due to the spring is to the left. Likewise, if I push the weight in and compress the spring, in this case, the force due to the spring is going to want to push it to the right, but my displacement is going to be negative because x of t is negative. So I'm going to have a positive force and a negative displacement. So what does this mean? This means that the force due to the spring is going to be the negative of the displacement, and since it's proportional, it's going to be something times that, and we're going to just call that constant k. And we're just being consistent with what they use in the physics department. So the force due to the spring is going to be minus k times x. So if x is negative, I'm compressing the spring. The force on the mass due to the spring is in the positive direction, so negative, negative is positive. If I pull the spring to the right, the spring force acting on the mass is trying to pull it to the left, or is negative. X is positive, this is negative, so the whole thing is negative. All right. So now let's look at the force due to friction. So I'm just focusing on the force due to friction, and I'm assuming this is proportional to the velocity in the x direction, because the y direction, it's not moving. So what does this mean? So if the mass is moving to the right, that means the velocity is positive, but the force due to friction is going to be in the opposite direction. So that means then that the force due to the friction is going to be negative the velocity, because it's proportional, it's going to be times some minus b. Likewise, if the velocity is to the left, that's going to be left movement. That means the velocity is negative, and the force of friction, again, is going to be proportional to Vx, but if the force of friction is to the right, it's got to be positive. So that means I'm going to need a negative times the Vx, and I'm going to use the same constant proportionality, so these things are consistent. So my force of friction then is going to be minus b times Vx. So from Newton's second law, I'm going to have the derivative of the momentum, and this is in the x direction, is equal to the force due to the spring. Let me make sure I get my signs right. What did I have? I'm just plus the force due to the friction. So I've got the time derivative of mvx is going to be minus k times x. That's my displacement. That's the force due to the spring, minus b times the velocity. And I'm going to assume for now that m is a constant. But just be careful. This is the thing that you need to be able to work with. If you get a situation where the m changes in time, you need to come back to here. So don't be surprised if you see that. But if m's a constant, I can pull that out. I've got that, and now I can add everything that's on the right. I can add to both sides. Let me write it as in this form. So I add bvx to both sides and add kx to both sides, and I get this. Notice, there's my x. X is a function of t. Vx is the rate of change of x. So that's the derivative of x. And the acceleration is the derivative of vx, is going to be the derivative of the derivative. So that's the second derivative of x. So what does that mean? That means then that's the second derivative of x, and that's the first derivative of x. So my differential equation describing the motion of the mass is this thing. And notice m, b, and k are constants. So it's a constant, coefficient, linear, second order differential equation. Okay. So let's look at an example. So for example, I've got a mass of 2 kilograms. It's on a horizontal table and is attached to a linear spring. And the constant is equal to 3. So we have k equals 3. And the force of friction is 1.5 times the velocity. So that means my b is 1.5. This information right here is telling me about the differential equation and what that's going to look like. The rest of this information is telling me what's going on with the system. So I'm going to pull to the left 1.5 meters, and I got to be a little careful. This should say right. Sorry about that. And the reason is because I'm pulling and not pushing or compressing the spring. And it's going to be released from rest. And the question then is, figure out x as a function of t. All right, let's focus on the differential equation first. The differential equation is in this form. I know that m is 2, and I know that b is 1.5, and that k is 3. There's my differential equation. If I'm going to pull it 1/2 meters from equilibrium, that means initially it's going to be at 0.5. So when t equals 0, the displacement is 0.5. And if it's released from rest, that means its velocity is 0. So you can think of it as I pull it out, stop, and then let go. So I've got my differential equation, and some initial conditions. And from this, I want to know what is x of t. Okay. Okay. We're going to put this off and get this later. But what's important for now is being able to set this up and recognize what it is you need to find. So in the near future, we're going to focus on how we actually find this. And we're going to basically make a guess. But for now, note that we have 2 derivatives. And because there's 2 derivatives, we need 2 pieces of information about what's happening. And then for our initial conditions, we're given the initial displacement and the initial velocity. And one way to think about this is because we've got two derivatives, if to undo this, you have to take two antiderivatives, and you're going to get two constants coming out. So you need two pieces of information. All right. As an aside, note that you're given K in this particular instance. There are other ways or other kinds of ways you could be given enough information to get K. So for example, instead of saying, giving you the spring constant, it could say something like, when the spring is displaced 0.25 meters, then the force is 5 newtons. So that's meaning that it's pulling at 5 newtons, and that's going to be K times that displacement. So that means that K is going to be 5 divided by the 0.25, which is going to be, 20 newtons per meter. Okay. Another way this information could be given to you is that we could say a 3 kilogram weight is attached to the spring vertically, and this displacement is 5, let's go with 0.05 meters. So the idea is you've got your 3 kilogram mass, you attach it to the spring, there's some force due to the spring, and then there's some force due to gravity. If this is at equilibrium, those two things have to match up. So the force due to the spring is equal to mg, and this is going to be minus kx, and I'm going to be careful here. In this case, my x is going to be negative because oops, that's not going to be right. I got to be careful here. Yeah. Sorry. I got rid of because I wrote it like this, I got rid of the signs. So I got the kx then is going to be equal to mg, and we're given that x is 0.05, mass is 3, so that says that k is going to be 3g divided by 0.05. Okay. So there's a lot of different ways to tell you what K is, and the same thing can go with B. For B, you can be given the force of friction, given the velocity, and from that, you have to calculate what B is. So you have to read these questions very carefully, ask what information are you given, and how can you use it to get what you need. All right. Real quick here, we're going to ask what happens if there's no friction. So what did we have? We had m x double dot plus bx prime plus kx is 0. If there's no friction, that means b is 0. So our differential equation is in this form. Intuitively, we would expect this thing to just oscillate. And if we don't see oscillations here, then that means there's probably something wrong somewhere. So in the next video, we're going to explore this idea and ask what this means. And we're just going to make a guess. We're going to ask, what kind of functions can we use if we have oscillations, and then go from there.